So, in my last lecture I introduced to you the Fabry-Perot interferometer, which is a fine instrument or a fine example of multi-beam interference. And what we had stopped at was finding the path difference for two neighboring beams. But as I told you, we have to find the total, we have to consider all the beams that are coming out of this Fabry-Perot interferometer. And a Fabry-Perot interferometer, as I had emphasized even before, it is a very important instrument. We will see some of its uses after I have finished the derivation. And I think the derivation, you should work it out yourself on paper and pencil, because while you are deriving, you get a very good understanding of what exactly is happening to the beam, okay? How it is getting reflected, how it is getting transmitted, and what are the angles between them. And once you know that, once you have got a judgment of that, you can use the Fabry-Perot interferometer in many places and many experiments. It's really a very good instrument, a simple technique, but very effective instrument. Okay. So, let us go back to the derivation. So, I had stopped somewhere here where the phase difference, I had stopped at the phase difference. Phase difference, so phase difference is the most important part of any interference pattern, is equal to k delta, capital delta is the path difference, 4 pi lambda upon d cos theta. So, here everything is known, d, the distance between the two plates is known, theta is this angle at which the input beam has come in. So, you know exactly the angle at which it is getting reflected, and lambda, of course, the wavelength of that light that you have used. So, all these parameters are known in your experiment. So, your phase difference becomes a known parameter. Okay. Now, let us consider the complex amplitude as a result of interference of n transmitted waves. So, n transmitted waves are there. So, wave E, that means the final wave, is a superposition of all these waves, E10, E20, E30, En0. So, as we have seen in so many other derivations in my previous lecture, superposition means you have to just add up all those waves, add up all those amplitudes and see what happens once you have added it up. So, here it is. So, I am going to add up E, E0 and all that. Now, E10 I have already said is sigma E0. Sigma is relates to the transmission coefficient and rho relates to the reflection coefficient. Okay. So, these are all the values which we have seen before, considering this, and E20 also we have written before, sigma rho E0, e to the power I delta. Here I have put in I delta because it is a wave, and any wave can be written either in terms of sine, cos, or sine and cos together, or in brief in terms of these exponential, a complex exponential term here. Okay. And this contains the phase part of the wave, and these are of course the amplitudes. Okay. So, here in the second wave, the amplitude is sigma rho square E0, and the phase part is embedded in e to the power I 2I delta. Okay. So, this is my complete wave, and so it goes on. So, until finally sigma rho to the power n minus 1 E0 e to the power I n minus 1 delta. Okay. So, this is my superposition of all those tiny waves together. I am using the word wave because I have not yet said anything about the intensity. Intensity we can always find out at the last step, because it is just square or E star E, you have just got to do that. So, let us find E. So if I take sigma E0 as common, I will get 1 plus rho e to the power I delta plus rho square e to the power 2 I delta plus rho to the power n minus 1 e to the power I n minus 1 delta. Okay. So this series looks very familiar to you, doesn't it? We've come across so many times this kind of series. It's just a mathematical series and we've got to find the sum of that. So, and instead n is actually very large. N is a very large number of rays. So, we can think of n to be infinite. Okay. So, an infinite number of rays interfere as they emerge out of the interferometer. So, the number of terms in the geometric progression, okay, this is the geometric progression, can be extended to infinity. Okay, this seems obvious. So many rays are there. N is just giving you just a number how to go ahead, but then n can be infinity. There are so many waves, there are countless waves, you can hardly count them. Okay. And using the mathematical summation for this, the convenient part is there is a mathematical summation for these geometric series, which goes up to infinity. Okay. And the expression becomes very compact. Okay. So, basically you use the mathematical summation S infinite is equal to A upon 1 minus R, where A and R are 1 plus R square plus R cube, that sort of a thing. This is the sum of series like 1 plus R square plus R cube, and the whole thing is into A. Okay, it's a series. The sum of that kind of a series is given by this. And I do exactly the same for our series, which is sigma E0, which corresponds to A, and 1 minus rho e to the power I delta. Okay. It's a nice little compact equation for my final electric field of that beam. After all those little beams have superimposed with each other. The intensity of the interference pattern, they have superposed and they have interfered with each other. And the pattern is then given by, see, when I say the interference pattern, I have to talk in terms of the intensity. So, let us do the intensity at this stage. I have found the electric field E star E divided by 2, that is the intensity, I is the intensity. So, if I just do this kind of an algebra, I will put this factor here, this equals to this factor, this whole total thing, just a bit of algebra is equal to this, and this part I have written in terms of cos. Rho e to the power I delta, rho e to the power minus I delta. I have just written this in terms of cos here. Okay. So, it looks like a simple equation which can be interpreted. Okay. Using the identity cos delta is equal to 1 plus 2 sine square delta by 2, and also rho equal to rho plus sigma is equal to 1. This is the conservation of energy which I introduced before. E0 square by 2 is equal to I0. I just call it, this is a constant factor. That means my initial intensity. Okay. Then this whole thing can be written in a nice little form like this. I is equal to I0, which is my initial intensity, 1 plus 4 rho sine square delta by 2, 1 minus rho whole square. Okay. Now, remember that in all this process I have got rid of the sigma part. That means the sigma part has been eliminated. So, we do not really have to think about the transmission coefficient at all. My intensity pattern depends all on the reflection coefficient only here, rho. Only rho, sigma is nowhere in the picture. Okay. So, all I need to do is those two plates of the Fabry-Perot, I need to know the reflectivity on the inner surface of those two plates. Once I know that, I know what is the interference pattern that is coming out of that Fabry-Perot. So, this is the intensity distribution pattern, this part. Okay. Actually, it tells a lot. Now, when sine square delta by 2 is equal to 0, okay, so this will give you some intensity pattern, and the moment there is a sine term, it is definitely an undulating pattern. That means points of bright spots, light spots, bright spots, dark spots, bright spot, dark spot, bright spot. Okay. So, it is an undulating pattern. So, you can very well imagine an interference pattern like that. Okay. So, now the intensity distribution pattern when sine square delta by 2 is equal to 0 or delta by 2 is equal to n pi. Okay, always sine square will turn out to be 0 then, okay, when delta by 2 is equal to n pi. Okay. Or delta is equal to 2 pi n, and n takes these integer values. Okay, don't think of n as refractive index, it is just an integer here in this context. So, then the total transmission observed is, suppose I put sine square delta by 2, this part is 0. So, total transmission observed is I max is equal to I 0. That means your maximum intensity of that pattern is your input intensity itself, you know. That is when sine square, the phase difference follows this equation. When sine square delta by 2 is 1 or delta by 2 is equal to pi by 2, this sine square part is 1, this part is 1. Okay. Delta is equal to pi 2m plus 1, again m is an integer. Then I minimum, this is I maximum. Okay. You cannot have light higher than your input intensity itself. So, this is the maximum. I minimum turns out to be, if I just put sine square delta by 2 is equal to 1, means I put 1 here. In this term I just put 1. Then what does this whole equation turn out to be? It turns out to be this. I only have those reflection coefficient factors rho, okay, and the input intensity. Okay. So, my minimum intensity is governed by the reflection coefficients. That means my minimum intensity is governed by the reflections of the inner surface of those two plates shown in blue, P1 and P2. Okay. So, here what will I minimum be? I minimum will be 0 when rho is equal to 1. Okay. Rho will be 1. That means you have a very good reflectivity, almost 100% reflection. Then I minimum is equal to 0. So, when your I maximum is equal to I 0 and your I minimum is equal to 0, this is the best interference pattern you can get. Okay. The visibility is the best then, the sharpness is the best, total intensity and in between 0 absolute darkness. So, the visibility becomes very good. Okay. So now we want to describe what this is, this factor. Not this factor, sorry, this is when it is I minimum. Just consider the factor here. Okay. You have a 4 row here, 1 minus rho whole square, 1 minus rho. So, this factor. If you introduce this factor, that means if you write A here, this equation becomes much more, it looks much more simpler. This itself is a simple equation, but again this will make it look simpler. But this factor has a very important consequence. Okay. So, I have put it here, A. It is called the finesse, F-I-N-E-S-S-E, finesse. A is called the finesse or the coefficient of finesse. Okay. So, just see why is this factor so important, because it only involves the reflectivity of the Fabry-Perot. And obviously, I can write that same equation as this, nice little neat equation, just put that factor A here, which is this. So, my interference pattern will be governed by this finesse. That means it will be governed by the reflective surfaces of the Fabry-Perot, and nothing else about the Fabry-Perot matters. Okay. So, we have these two glass plates. You have to just see what is the reflectivity of these two plates. Okay. Glass plates or anything that is transparent to the light that or to the wavelength that you are trying to measure or you are trying to get an interference pattern with. Okay. So, if I just go back to that first picture, see, it is simple, just two plain plates with a distance d, and I just have to bother about the reflectivity of this inner surface of these two plates. I do not have to think about anything else in this instrument. I do not have to think about anything else in this device, which will give me an interference pattern, and those interference patterns have very good consequences also. Okay. So, I started off with this multi-beam interference through amplitude division, and now I have got a interference pattern at the end, interference patterns which is caused by this transmitted light. I am taking the interference of this transmitted light, but that interference pattern depends on the reflectivity of the inner surface. Sounds a bit strange, but okay, that's how it works. Okay. So, I come, this is a very important coefficient, finesse. So, if here I have just put in one diagram which depends on the finesse. In this diagram, this purplish one, A is low, that means the finesse is low, while in this brownish diagram, brownish reddish diagram, A is high, that means finesse is high. Okay. So, you can see, this the brownish one is a very sharp pattern, and this green one is okay, not that sharp. This part is not 0. In the brown one, the minimum part is almost 0. So, whenever the minimum part is almost 0, you get sharp interference fringes. Okay. So, if these two are the sharp interference fringes, and between these two there is almost 0, and that happens when A is very high. Okay. So, when is A very high? Let us see what, suppose this rho is equal to 0. Okay. Then what happens? Rho is 0 means A is equal to 0. Okay. A equal to 0 means in this equation I by I0 becomes equal to 1 upon 1, okay, 1 plus 0. So, I is equal to I0. That means whatever was my initial intensity, the maximum intensity occurs at I is equal to I0. So, actually it corresponds to this point. This point here, and this axis is the delta. Okay, I equal to I0 comes at a certain delta. Okay, let us see what that delta is. At a certain value of delta, say it was the maximum, this maximum, I is equal to I0. It corresponded to a delta of 2 pi n. Okay. That was the delta part. Now, I am talking about the finesse part. Okay. It is at this point you are getting maximum for all of them, but your A may not be as high as this. So, the delta for all these three graphs is the same, but the finesse is not the same. So, if the finesse is either high or low, you are going to get a blurring of the pattern. You can see it here. The minimum is not 0, this minimum is not 0. You do get a peak, you do see some pattern, but the visibility is not so good, or there is a blurring. Okay. I call this T is the transmission, is I upon I0 is the transmission. So, I upon I0 transmission is maximum when I is equal to I0, or transmission is equal to 1. Transmission is equal to 1. Let us see what happens when the transmission is half. Okay, so I upon I0 is equal to half. When will that happen? When A sine square delta by 2 is equal to 1. Okay. A sine square delta by 2 equal to 1. If I go back, sine square delta by 2 equal to, sine square delta by 2 is equal to 1 when delta is equal to pi 2m plus 1. Okay. So, all right. So, then I by I0 will become half, okay, when this factor becomes 1. So, that means we will find the transmission to be half here or 0.5 at this level. So, when the transmission is half, you are really not getting, you are not getting such a sharp picture again. Okay. So, suppose I consider sine square delta by 2 is also 1. So, A will be 1, suppose A is 1, the finesse is 1. So, 4 rho by 1 minus rho whole square equal to 1. Okay. So, from here I can calculate the rho. That means I can calculate the reflectivity, okay, which can be easily, and accordingly I will get that reflectivity of my Fabry-Perot. Okay. I will stop here, we will go on further about the Fabry-Perot, which is such an important instrument.